Hello, everyone. I'm still pulling some things up. This Hangout is one that I'm going to apologize right off the bat. We are experiencing some various technical difficulties as we go. But hello and welcome to this Inspiring Science Education Hangout. This series is one that strives to bring you regular content on big ideas in physics and astronomy. My name is Dr. Pamela Gay, and I will be your host for this episode and this entire series, and I hope to see all of you coming back and learning more week after week. Today's episode, we're going to be talking about the interplay of gas, gravity, gas pressure, and basically how it is that gas is tortured by various events throughout our universe, from supernova to gas getting compressed down in the hearts of galaxy clusters. The format for this hangout is going to be about 30 minutes of talking with two wonderful experts that we have joining us who work with the XMM Newton X-ray Observatory. And then we're going to spend about 30 minutes talking about a lesson plan that we have posted that you can use up on the Inspiring Science Education community portal. With me, well, actually, before I introduce the scientists, I'd like to let you all know that you can actually participate throughout this entire Hangout. If you are watching this live, wherever you're viewing it, you should see a little yellow Q&A icon on the window. If you click on that, you can leave us messages, ask us questions, and participate through the show. I will be monitoring that, so feel free to ask what you're interested in as we continue through this episode. Now, joining me today, I have Martin Guerrero, and I'm sorry, my Spanish is poor, who joins us from an institution I cannot pronounce in Spain. And also I have with me Jacco Vink, who is joining us from the Netherlands. Welcome, gentlemen. Thank you so much for coming on today. As a start, the two of you work on two very different processes that both demark the end of a star's life. Can you both sum up what it is that you're looking at and where that gas that we're studying comes from? Jacco, I'm going to start with you, and apologies to the audience. Google Hangouts won't allow his lower third to let you know who he is, so I'm going to say his name a lot. Thank you, Jacco. Can you tell us a little bit about your work? Can you hear me? Hello? Martin, can you hear me and say something?
Yes, indeed. It's a pleasure to be here to talk to you about science and to join the community that want to learn things about our universe.
So we're trying to sort out a technical difficulty. Jacco is currently hearing an echo. I suspect what you're hearing, Jacco, is that you have a window open somewhere on your computer that has this Hangout playing. So if you have, for instance, the Google Plus page open, that may be the problem.
I see that his microphone is muted.
He shouldn't be muted. Yes, there. I'm unmuting you. I'm trying to unmute you. It's not letting me unmute you.
No.
So we're trying to. Oh, now I hear myself. I see why you're muting. Okay. So yes, Jacco, the problem is that you have a window open somewhere that has the Hangout playing in the window, which is where you're also getting a 5-second delay. I'm going to type that to you so that if you're... So sorry, audience. This is one of those things that happens sometimes. Okay, Martin, while Jocko is working to sort out his technical difficulties, could you tell us a little bit about what it is that you study?
Well, I'm interested in the life of stars and actually in the end of their lives when they are going to leave their envelopes in the interstellar medium so that we see how our solar system or our sun itself is going to be evolving within 5 million years. So that's called a phase in the stellar evolution called planetary nebulae. Well, this is basically what I study.
So, stellar envelope is one of those things that sort of makes one imagine taking a
Mm.
star and sticking it in a UPS envelope and shipping it across the universe.
Mm.
What does stellar envelope actually mean?
You know, a star is consisting of different layers of material. So you have the nuclear burning at the core of the star, and then most of the material is like a plasma, hot plasma surrounding this core. At some moment in the evolution of those stars, those are low and intermediate mass stars, stars like our sun. They kind of get tired of all this material, and they start to shed all this material into the interstellar medium. Basically, they grow too much that the gravity cannot pull the material into the star, and so it starts to flow away into the interstellar medium. And so this is how, in kind of a quiet way, I like supernovae that Jaco is going to be talking about. So this is in such a quiet way as those stars are going to end their lives.
So the easiest way to think about it may be that uh, these stars, they essentially blowed up and then just let go of the outer layers, the fluffy atmosphere parts, not the actively burning and
No,
producing light nuclear parts.
no, not definitely. And as this nuclear region gets exposed, so conditions are going to change. Basically, as the star is shrinking, you are getting closer to the core, the gravity of the surface is increasing, and so the escape velocity is going also to be increasing. I mean, the velocity of a particle in order to escape from the star needs to be increased, and this is going to produce an acceleration of the envelope of the material which is being ejected. So we are going to have kind of material moving at different speeds, and when you have different speeds, you get shocks. And this is what we see inside a planetary nebula.
Now, you're working on a much more energetic process, Jocko. Could you tell us a little bit about what you're working on?
Yes, so I'm working on supernova remnants. So this is what is left behind after an explosion of a star. These are massive stars, so stars more massive than 8 times the mass of the sun at the end of their lives. They have converted their core into iron. They cannot get energy out of that anymore, and the core collapses and forms a neutron star, a very energetic object that we can see. But while this is forming, energy is released mostly in the form of elusive particles called neutrinos, and about 1% of this energy is transferred to the rest of the star, and the rest of the star starts expanding with speeds up to 20,000 kilometers a second, and it slingshots all this material into the gas in between the stars, or maybe into the stellar wind of the star that was once there, and this creates this very energetic material, this material with very high speeds, creates also shock waves which heat up the gas to very high temperatures, say millions of degrees Celsius, that is, and then it starts producing X-rays. And in those X-rays, we see both the material of the wind or the circumstellar medium, the medium that is out there, the gas that's out there, plus the gas that is coming from the star itself that exploded.
Now, these are just two of the many different ways that astronomers study gas in our universe. When we look at space, the bulk of what we see with our eyes are stars that are here in our own Milky Way galaxy. really dark site, you can start to see some of the star-forming regions, like the Orion Nebula, and other pockets of gas and dust that are in our own galaxy. And if you're someplace dark enough in the northern hemisphere, you can see the Andromeda Galaxy, and if you're somewhere dark enough in the southern hemisphere, you can see the Large and Small Magellanic Clouds. Other than that, I mean, really what we mostly see is just stars, but a lot of the mass in our universe is still just kind of hanging out in pockets of gas. We have gas that comes from ejecting stellar envelopes, the atmospheres of stars in supernovae that come from the more quiet process of just letting go in planetary nebula. We also have all of the gas that hasn't quite made it into a star yet, and this is where we start looking at the gas that's around stars like Wolf-Rayet stars, which are very high mass, very young stars. Martin, I know you worked on Wolf-Rayet stars in the past. Can you tell us a little bit about these?
Well, basically we see very similar processes in Wolf-Rayet stars as in planetary nebula. They have the most powerful stellar winds in the stars that you can see. So they lost a large fraction of their masses, something like one solar mass in just 10,000 years. And the speed of this stellar wind is also very high, it's like several thousand kilometers per second. So in just a few seconds, material expelled by this star can go through the diameter of the Earth. So that's really fast. And so these particles, they have a significant fraction of energy. When when that material is impacting, is crashing into the previously ejected material from the star, this is going to blow bubbles. When this happens, we have a shock, which is actually a forward shock, which is pushing material away, but at the same time there is a backward shock. There is a shock inside the stellar wind, and this is going to heat up the stellar wind and produce very hot, a very high temperature, up to several million Kelvin temperature, and produce X-ray emission. Actually, if you study those sources, if you study the envelope, the surrounding of Wolf-Rayet stars, actually you are going to see what's going to be the place where supernova are going to explode. So when a supernova is going to explode, it's going to interact with all this material, and so this is a topic where Jaco may add something.
Jaco?
Yes, so certainly those supernovae go off in this very complicated environments. And I must say, most supernovae, they all appear different, and that is probably caused by the variety in environment. So a Wolf-Rayet star, you probably have a rather evacuated region, and it may be that you get a very bright supernova, and it's only when the shockwave is at the end of this wind, because the wind is not that has a very tenuous gas density. But you also have, say, red supergiants. They have also not so much a strong wind, but they lose a lot of mass, but very slow, and you have a much more dense wind. And there you get early on a very bright supernova remnant. So there's a lot of variety there that is caused by what is happening before the actual explosion. So supernova remnants highlight both what was inside the exploding star, but also what happened, say, the last 10,000 years before the star exploded.
Now, when students in school are learning about gas, what we're talking about is gas that is in sealed containers that we're changing the volume of, that we're changing the temperature of. Space is a little bit more open-ended, and what we're dealing with is a whole lot more complex, but the same physics that we deal with here on Earth is the physics that we deal with in outer space. When we're looking at the gas that's given off in planetary nebula and supernovae events, we're looking at gas that is getting heated, it's getting shocked, which is a fancy way of saying that it's getting hit either by a whole lot of light coming off of the object or by the material that came before it moving at a higher velocity. So the way to think of that is if you blow on something, the start of your breath hitting it is a shock wave.
Yeah.
And if you do this on a cold day, you can see actually that breath coming back towards you, and that is part of the shock wave of your cold breath, except when stars do it, it's the same physics at much hotter, higher velocities. Same physics, different scale. Now, what all does the gas in these different things experience? You have the heating that's coming from the light. You have the increase in velocity. Can you take us through these processes? Martin, I'll go to you.
Yeah, well, in the case of planetary nebulae, you see those beautiful objects which are illuminated by a central star, so they get ionized, and you see those mainly in optical emission lines in the optical. So you see those pretty pictures produced by HST, or even with your small telescope, you can see those planetary nebulae, those greenish discs that you see in the optical. So this is the ionized material. And this is relatively hot material, maybe 10,000 Kelvin temperature, but compared to what's inside, what's the shocked stellar wind, this is relatively cold. So you have a phase, like a shell of, we call cold material, but it's 10,000 Kelvin, and inside there is what's called the hot bubble, so very, very hot material with a very large thermal pressure, and this is pushing away the material. So it's similar to what you say when you have your when you blow your hand and you see those flow of material. So in this case, it's the same. You have the escaping wind from the center star, which is shocking the optical nebula, and there is this forward and backward shock. But the difference here is that you have material that they have like 100 times difference in temperature. So you have 10,000 Kelvin, 1 million Kelvin, and so there are additional physical processes here. So you have heat conduction. So the heat from the material inside somehow is put into the outer material, and those are mostly electrons, the teeniest particles that they move very fast, what can produce this heat conduction. But there is always turbulence, so material they are mixed in some kind of turbulent mode. So in this way, we used to say that planetary nebula are ideal physical laboratories. So we can study a lot of physics by looking and investigating planetary nebulae.
Now, we have lots of stunning images that we normally use to try and study supernovae and planetary nebula as well, and these tend to show that this isn't a completely smooth process. I'm going to bring up the Eskimo Nebula as a starting point, and let's try and talk about some of the different things that we're seeing in these images. And one of the things I think a lot of people don't understand is one of the main motivations for building the Hubble Space Telescope was from the Earth, these objects look like really confusing smudges on the sky. And we built Hubble in part to try and understand what are these confusing smudges. And this is one of my favorite confusing smudges. So let me pull this up. So can you tell us a little bit about what we're looking at, Martin?
Well, there you see in blue, this is what I call the hot bubble. This is material which is emitting in X-rays, and this is confined within a closed shell. So this is what was the envelope of the star ejected, that was expanding at a very slow speed, and which is now accelerated by the thermal pressure of the hot gas. Outside, you see some kind of fainter emission, very, very naughty, and this is the material ejected in previous phases of the stellar evolution, which has not yet been, has not interacted with this fast stellar wind. So actually, here we see not only the details of the structure of the object, We don't only see the hot gas inside the Eskimo, but if we compare images taken with a time lapse of, let's say, 10 or 5 years by the HST, we are able to see even the expansion of this shell. So we see really the dynamics there, how the shape, how the different filaments there are changing, are evolving with time. And this is something that it's really HST the only telescope that can make this kind of observation, that can enlarge our understanding of the dynamics of the gas in the interstellar medium.
Now, we find as we look through space that all sorts of different things look different. This is another cloud in the Large Magellanic Cloud, which is a nearby small galaxy. And then we also have supernova remnants like this one. This is the Kepler supernova remnant, which is named because it was Kepler who actually observed the supernova when it went off. So this is something that we've got to watch evolve over human generations. Can you explain what we're looking at here, Jack?
Yes, so we see here indeed the Kepler supernova remnant. It's a rather special supernova remnant in the sense that it is rather high out of the galactic plane. So the star that exploded there must have had a velocity of about 100 to 200 kilometers a second before it exploded in order to come that high. Now you see a sort of peculiar morphology, and the bright side is actually the side in which it is moving. And that is because the gas coming from the star while it was moving, the stellar wind, was crushed on one side because of the motion of this star. And now this shock wave from the supernova is crushing into this. And you see several images there in different colors. And what is striking about this supernova remnant is how much iron there is in the supernova remnant. So iron actually is material that can only be made in supernovae. So all the iron around us was once part of a supernovae, then of a supernova remnant before it sort of mixed with all the other gas, and out of that gas, that type of gas, we are ourselves formed. So the speciality is, of course, that it is indeed young. It's observed by Kepler and others in 1604. And it is very special because it's very high above the galactic plane, the Milky Way plane.
So many different supernovae have been actually observed by humans when they went off, and we now get to observe them down through the generations. We also have Tycho here, and it looks radically different. It's looks actually kind of like something you might see in biology rather than astronomy. Yes. Can you help us understand why this one looks somewhat different?
Yes. It's always hard. As I said, they all seem to have other environments. So Kepler supernova was mostly formed by this wind that was already moving with a lot of high velocity. This probably took place in a more quiet environment. So maybe it had a little bit of a stellar wind, but not much. And that created a much more round supernova remnant. What you see in green here is mostly silicon, and what you see in red is iron again. And now this blue is very special because these are actually electrons that have a lot of energy, about the energy that particles can get in the LHC at CERN. And then it starts, because it's moving in a weak magnetic field, it starts also producing X-rays. And this has to do with something that we call cosmic rays. So Earth is bombarded by very energetic particles. This is what causes actually, an increased chance for cancer, say, for pilots, because they are high up in the atmosphere. And these particles are probably accelerated in those shocks. So that's why this bluish thing is only at the edge of the supernova remnant. So that's where the particles are being accelerated. So we don't see, this blue is not hot gas, but this is extremely energetic electrons.
Now, as we look at different objects, what we find is planetary nebula have even more variety to them in some ways than supernova remnants do. And this actually has to do with the fact that these are somewhat less destructive in how they're created.
Mm.
Can you give us any insights on what it is that what factors lead to these different structures in planetary nebula, Martin?
Well, the basic idea, what's called the canonical model for formation of planetary nebula, it's what we call the interacting stellar wind model. So basically, we have this wind from the late evolution of the star, which is massive, is slow, and which is going to be now swept up by the fast stellar wind. So if you have two stellar winds and they are spherical, then you are going to produce a shape which is spherical. But what happened if, for instance, the previous stellar wind was not spherical? So if there is more material along the, say, the equator or some particular plane, then you are going to have some structure which is going to constrain the expanding stellar wind. So let me show you the ultimate planetary nebula modeler, which is this one. I hope people can see that. So if you have two stellar winds and they are spherical, so they are going to produce a spherical planetary nebula. But what happens if you have more material along a plane? Then this is going to compress the expansion, and then you start to have shapes which are axis symmetric. If you have more and more material at the equator, then you are going to produce bipolar structures, something like this. So this is the basic way where we explain the different morphologies of planetary nebula. There is something more. There are more, because in some cases we can see kind of collimated outflows or some additional features. But this is the canonical model, which is able to reproduce most of the morphologies that we see in planetary nebula nowadays.
And it's important to note, even though we don't have a photo of it, that this bipolar structure also appears with supernovae. We saw it in supernova 1987A, for instance. And one of the reasons we don't always see it clearly is when we're looking at these different images, the alignment matters. And if you're looking at something that's figure-8 shaped, but you're looking at it down the top or from the bottom, depending on how you want to consider it, you're not going to see that awesome bipolar structure. We also, in looking at these different images, don't always think about the fact that what we're mostly looking at is the outer parts of a mostly hollow sphere. So for instance, when we look at this particular supernova remnant, I think this is a supernova remnant, that green ring, that is actually the edge of a shell. And just like when we look at soap bubbles, we don't generally see the front and back of the soap bubble. We see the edges where we're looking through the greatest thickness of material. When we look at these bubbles in space, we're also looking at a shell where we mostly see the edges. Can one of you tell me a little bit about this image that I just pulled up?
Yeah, actually, this is not a supernova. It's a Wolf-Rayet bubble, a wind-blown bubble around a Wolf-Rayet star. It will become a supernova sometime in the future. But what we see there is indeed a shell here in green and yellow and red. It's different emission lines. So we see the optical emission. We see what I call the cold material, and what's inside in blue is the hot material, the X-ray emitting material. Actually, you see that this is basically like a round shell. So when you see the line projected, you see what's called the line brightening. So you see more emission along the line of the source. But basically, this is like an empty shell. What's here is interesting is that the material, the circumstellar material, is very important. So when you have gas and you have a container here in the Earth, the container has a definite shape. But out there in space, we have the container of the hot gas is actually gas. So it can get different shapes. And when there is one point which is weaker, When there is somewhere which is emptier and so material can flow along this direction, it's going to produce this kind of blowouts that we see in the top of the images of this image. So we see that this is mostly round, but at some moment in the upper right corner of this bubble, we see that the gas has found a escape, a way to escape from there. And so this is like blowing this, producing this blowout on top of the shell.
That is a really amazing story to think about. And one of the things that I've always appreciated is when you look at the sun, the edges of the sun appear to be darker because of limb darkening. In this case, the cool atmosphere, you're looking through more of it when you look at the edge of the sun. But with planetary nebula and other essentially bubbles in space, like the bubble from the Ray A star, you have limb brightening because you're looking at a greater amount of the brightened material. So same idea, in one case shadowing and in one case illuminating, and that's just kind of fun to think about. Now, the one last place that I'd like to go in our discussion before I move to talking about the lesson plan is gas that's near and dear to my heart, and this is gas that is in the center of galaxy clusters, and this is some of the hottest, long-lasting material that's out there. Can you tell us a little bit about what gas is subjected to when it falls into the center of a galaxy cluster?
Well, you know that a cluster of galaxies, they are the most massive structures in the universe. Actually, a significant fraction of their mass is in this dark matter or dark energy which is associated to the cluster. So basically, there is a large amount of mass there which is pulling from the galaxies so that they keep rotating, they keep orbiting the cluster of galaxies. So all this amount of mass, they are going to produce a very deep gravitational potential. So it's very difficult to escape from a cluster of galaxies. So anytime one galaxy goes near to other and it gets some material from the galaxy, it's going to be trapped in this potential, in this gravitational potential. So what happened? Material is going to go into that potential because it needs to keep itself, it needs to increase its pressure. So the only way you can keep the pressure in the gas is by increasing its temperature. So finally, you have material at the center of the cluster that, in order to be able to sustain its own weight, needs to be at a very hot temperature, up to 10,000 or even higher million Kelvin. So material is so hot that it's going to be fully ionized and it's going to produce emission in X-rays. So actually, X-rays is one of the ways to not only detect cluster of galaxies, but to study the distribution of material inside of cluster of galaxies. So we see here different morphologies of cluster of galaxies, and this is associated to how material is distributed into this cluster.
So the image I just pulled up is a set of Chandra images of a variety of different galaxy clusters where the purple is the site of X-ray emission. This is another rather famous Hubble image of a massive galaxy cluster overlain with, again, the purple for the X-ray. And you can see that the density of the gas does increase as you get closer and closer to the center of that gravitational potential well.
Yeah. And actually, the funny thing, Pamela, is that what you see there is just by maybe 10 or 20% of the total mass of the cluster. Most of the mass, like 80 or 90%, is this dark matter that we don't see. We cannot see directly in images, in neither wavelength that we look at the cluster of a galaxy. There we see galaxies, we see stars, we may see dust, and we see the hot gas through the X-ray emission, but most of the material is not seen.
So we've covered a whole lot of topics, and I've kept you both longer than I had said I would. Before
No
I
problem.
let you go back to your evenings, and thank you for taking your time to join me this evening, um, what would you say to a kid that was thinking about studying astronomy? What would you do to tempt them into the bright side of X-ray astronomy? I'm going to go to you first, Jacko.
Well, what I like about astronomy in general, and maybe X-ray astronomy in particular, is that we're looking at very extreme things. I personally like physics very much. How are things working? And if you want to see how things really work, you want to go to the most extreme standpoints, high shocks, high velocities, very high densities or very low densities. In the extremes, you see, what something is really worth. And with X-ray astronomy, you're looking really at things that are at extreme temperatures. So you see how gas is behaving when it is very hot. Something it's very difficult to study here on Earth. So by looking at space, you can see nature at its most extreme, and this is intriguing me, and I hope this also intrigues kids.
So what would you say to lure people into your area of research, Martin?
Well, I quite agree with Jaco that we are when we do research in X-ray astronomy, we are looking into the matter when it reaches the most extreme conditions. Actually, there are many of those conditions that we cannot reproduce here on Earth. So we see phenomena, we see physical conditions which we cannot study here. So this is like opening a new window to the physics, and this is something that can be done using the X-ray astronomy.
So this has been a wild conversation peppered with odd technological glitches. I thank you so much for your patience. I know this hasn't always been an easy hangout to be part of. Where can people learn more about the work you're doing if they want to look you up online? Martin, I'll start with you.
Well, I used to post my research mostly on the web pages of Chandra and XMM Newton. So there you'll find a lot about bubbles around the central stars of planetary nebulae, bubbles around Wolf-radiated stars. There is a lot of physics there. So if you are interested not only in inspiring images, but also in real physics of how gas behaves, how gas mixes, and how gas behaves when it's taken into very extreme conditions. So you'll find very interesting information there. Besides this, well, my institution, the Instituto de Astrofísica de Andalucía, I know it's difficult to pronounce for non-Spanish, there you'll find my work there with many more colleagues of mine working here.
Thank you. And Jakovic, who Google will not let us know your name, but I know your name, so I'm going to share it out. Where can people find you?
You can go to my website at the University of Amsterdam and find some of the work I've been doing. Whenever there is a press release or something out there, I try to summarize it in more explainable English, less technical, although still quite technical. And some of my images have been posted indeed on the XMM website. So some of the images that you showed were actually from this website and come from me and my direct colleagues.
And we'll work on getting links to all of this posted out in the notes for this Hangout. Thank you so much for joining me. If the two of you want to take off, you're free. And the way you do that is there's a little red hang up button at the top of this. But I'm not going to hang up on you, audience. Instead, I'm going to tell you a little bit about the lesson plan that we've put together. And everything that we do can be normally found at the Inspiring Science Education website. I unfortunately have to admit that right now, if you try going to this website, this one will work. So this is the landing page at www.inspiring-science-education.net. And when you get to this site, what you want to do is click on Community Portal up here in the top right. But unfortunately, right now, I'm hitting a website not available issue. So I know they're in the process of doing some amazing site updates to enable you to better search, better find resources. This is a work in progress, and unfortunately, it just happened to be that the time that we're recording this Hangout, this is a live event. Sometimes things go sideways. Happens to coincide with one of those times when you're doing a site update. Um, if you could log on, what you would find is both well, first of all, what you'd find, sorry, I'm looking to see if I still have the window open. Yes, I do. What you would find is a list of different communities that you could join. And one of the communities that you can join is the Discover the Cosmos parent community. So you can see it's listed right here. And once you join the Discovering the Cosmos community, that's the community that we're using for all of the classroom curricula hangouts that we do. So everything that you learn about through these inspiring science education hangouts, those are all listed in Discover the Cosmos. Now, within Discover the Cosmos, we have a variety of sub-communities, and gas laws with stars and nebula, well, that's what we were talking about today, and this is the community for today. Now, I was hoping to now go ahead and show you the lesson plan that we posted this morning, but unfortunately I closed the window that lesson plan was in, and because they're in the process of upgrading this site, I can't get back to it. So I'm just going to have to tell you what's in it, and hopefully you'll be able to get to everything shortly. Now, one of the things that we got feedback on with past lessons was you were hoping to see more exciting ways to start each lesson off with your kids. And we heard that feedback and we responded. So with this lesson, instead of starting out with vocabulary to go over, what we start you off with instead is a TEDx educational video, sorry, not TEDx, TED-Ed video on the ABCs of the gas laws. And this particular video is a very simple video that was put together by Brian Bennett. And this video goes through and talks about Avogadro's law, Charles' law, Boyle's law, all the different laws that together were discovered empirically, discovered through experiment. And once they were discovered, we were able, as a scientific community, generations before I was born, to figure out the fundamental gas laws that we use to understand how gas responds to changes in temperature, volume, and pressure. So you can start off by showing this really simple, really straightforward video to your kids. And within the video, it talks about a variety of different experiments that you can do. The first one is you just take a bottle and you squeeze it and the lid pops off. And that shows how pressure increases as volume decreases when temperature and amount of gas is held constant. And in fact, the pressure increases enough that it will pop the lid off of a container. It encourages you to take a balloon and add air to it. You're increasing the amount of stuff in the balloon, you're increasing the pressure, you're blowing up the balloon. And the next one's kind of hard. It's the how does volume increase when you increase the temperature of a gas? We've all probably seen this either in real life or on TV, where hot air balloons are able to lift off and fly away when the gas inside of them is heated, and it increases in volume, decreases in pressure, and decreases in density, and this lower density material, this lower density gas, causes the balloon to have a greater buoyant force acting upon it so that hot air balloon floats up. Well, this lesson doesn't actually get into buoyant force, so we don't care about buoyant force. What we care about is that set amount of gas increasing in volume when we heat it up. And easy ways to do this are you can take a plastic bag that has a little bit of air in it and stick it into boiling water, and it will bloat up. You can take a hot container of your lunch to class with you, set it on the counter. You may not want to do this because you may not want to eat your lunch afterwards, but that hot food with air above it in a sealed container, the lid will suck itself down in. And I think my favorite example of gas expanding is that bag of popcorn that you stick in the microwave, and that paper bag bloats up even before the popcorn starts popping. So in that key moment before the popcorn starts popping, the air expands, and it's the air that starts to increase the size of the bag. So we'd encourage you to start out by showing this video, by showing your kids actual examples of the gas laws in action. Now, in trying to help them understand how these gas laws apply to the universe around us, this lesson is perhaps the most math-intensive lesson that we're going to go through. And this is your chance to say, if you're going to be a scientist, you actually need to be both math and computer literate. Because not only do they have to do the math, but then we're going to have them build a very simple simulation on their computer. So the starting point for the math, and here I was hoping to show you, we've provided you in the teacher notes for this lesson the complete derivation that we're going to ask your kids to do. So you don't need to worry in the night before you're prepping, you don't need to worry about redoing this every single time, because if you're like me, you're going to periodically lose your notes. We've provided you the complete solution. What we're going to have you do is have your kids start off with, well, let's imagine a cloud of gas in space. Now, real clouds of gas in space, I'll pull up a picture of one. Here we're talking about cold clouds, not the ones that are caused by supernovas, not the ones that are caused by planetary nebulas, but the ones that are made up of just leftover material that's out between the stars. Now, these actual nebulae, and this one's called a Bach globule. Actual nebulae are kind of lumpy. They have variable density. They're complicated systems. But for the purposes of doing this lab with your students, we're going to assume a perfectly spherical blob of gas in space, and we're going to start by assuming that the density of the gas is constant throughout that entire blob. Now, as a starting point, and make sure your kids know this is all estimates done to make this a simple problem. Actual science, in this case, is unfortunately much more difficult and requires all sorts of calculus. In this simple toy model, imagine that you have this sphere of material. Well, think about life on a plane that cuts through the center of that disk of material. You have a pressure that you're experiencing that comes from the gas above you exerting a pressure on that plane, the gas below you exerting a pressure on that plane. Well, pressure is force times area. We know the area of that plane, which means that we can start to make a calculation of what the force is that is exerted by the top half of that sphere on the bottom half of that sphere. That's just an equation. You can start with the gas law equation for pressure. In this case, we want to use the one that looks at the number density of the material. You tell your students, we're going to assume that this is a 10,000 star mass, 10,000 solar mass gas cloud. And let's assume it's made entirely of hydrogen. Well, if it's molecular hydrogen, we can solve for the mass. Well, actually, we can look up what is that mass of that molecular hydrogen. If we know the total mass of the cloud, we can now solve for the number density, the total number also of molecules in the cloud. And if we know that, now we can start calculating pressures. If we know the pressure, we can start calculating forces. Now it's just algebra. So you chew through the algebra and you have each of the students work on this independently. Then let's figure out what's the force that top half of the material is using to press down on the bottom part. But let's make this interesting. Let's assume we want to solve for when pressure and gravity are equal to one another, such that the gas pressure that's trying to push out on this cloud of gas is balanced by gravity trying to collapse that cloud back down. So let's figure out what the force is and then set it equal to the force that's being exerted by gravity. Again, all of this is detailed in the assignment. The bottom line is you can have your students solve for that awesome situation where the gas pressure is balanced out by the gravitational pull. So you have pressure over area exerts a force outwards. You have gravity exerts a force pointing inwards. Balance this out, and you can, in our toy model that is very simplified, start to figure out at what radius is this a stable system. Now, I'm going to screen share with you the spreadsheet that I set up to do all of this. And let me zoom in on that a bit so that it's a little bit more readable. So we're going to have the kids work to set up a spreadsheet like this. So here we have all of our variables up at the top. I converted my mass of the cluster, my mass of the cloud into kilograms. This is going to have a lot of unit conversions. In the problem, it says that we're going to assume the gas cloud is about 15 degrees Kelvin. This is the type of temperature that we're often looking at for these clouds. I provide the Boltzmann constant, the gravitational constant. This is the mass in kilograms of a hydrogen molecule. And just to make things interesting, I'm going to make it so that we can convert from the meters across this cloud is going to be to the number of light years. Now, in our toy model, what we can find when you do all of the algebra, again, everything is derived in the assignment. You can solve to get this equation right here for the gas, this equation right here for the gravity. When you set those equal to each other, you find a starting radius that's kind of huge. You find a starting radius of about 772 light years across. Now, the next thing that we're going to ask the kids to do is figure out what happens if we take this happy, in equilibrium cloud of gas that's neither expanding nor contracting. It's just sitting there being a cloud of gas. What happens if some external force comes along, like the shock of a supernova, like we talked about with the scientists? What happens if it comes along and reduces the radius of the cluster to be 95%? So at 95%, we're now at a somewhat smaller radius. And suddenly we see that the force from the gas, it goes up. That's to be expected. We decreased the volume, the pressure is going to go up. But gravity also went up, and gravity actually went up faster. And if you step through and you follow through what's happening, going down to half of that original radius, and you make a plot. Here's our starting point over on the right at maximum radius. As the radius decreases, what we find is the force caused by the gas pressure does increase. And in this toy model, we're ignoring increases or decreases to temperature. It would actually increase and then radiate away some of that increase in temperature. So we're ignoring the increase in temperature. In our toy model, we find that the gas pressure goes up, but the force of gravity goes up even faster. And since the force of gravity, which is trying to collapse this cloud, goes up faster, in response to the reduction in radius than the force of gravity. There's no force that allows this cloud to expand back out to that equilibrium point that it started in. Instead, at an increasing rate, the cloud is going to contract and contract and contract. And this is what your students are going to get to figure out for themselves through this very math intensive lesson. Again, we've provided you the full derivation, and it's actually at a level that your kids can do this entirely on their own. But it's really easy to make algebra mistakes. So this is where, as I said, we're going to have the kids each solve for the equations on their own, but then we're going to put them into groups to work on the simulation in the spreadsheet. And before they start working on putting together the spreadsheet, they're actually going to compare the results among one another and figure out, okay, which of us got this right? Oh, good, we all got it right. Oh, wait, no, we didn't all get it right. Let's figure out what the right answer is before we move on. And one really cool thing that you can point out is the units on all of your constants. So the Boltzmann constant, the gravitational constant. If you check all of your units, if you did all of your algebra right, then the radius has units of meters. And if you didn't do all of your units right, if you didn't do all of your algebra right, the units aren't going to work out. Now, when you hit the end of this lesson, this is where you explain to your students that, yeah, we know this was really simplified. Actual clouds are much more complicated. So here's an example. This is the Bach globula, as I pointed out. But we also have the ever famous Messier 16, the Eagle Nebula, that has within it these pillars of creation you can see down here in the lower right. These pillars of creation appear very different depending on if you look at them in visible light, where you can clearly see the dust. If you look at them in the near infrared, where you can start to see through the dust to see where stars are forming inside the pillars, or look at them in the mid infrared, which allows you to start seeing where the star formation is actually heating this gas up. Actual work has to actually try and understand all of the crazy lumps and bumps and ways that our universe collapses clouds of gas to form stars that is so much more complicated than what we see in this theoretical model that we have your kids do. And to help the kids understand all of this, we've actually included a really neat article that talks about all of the destructive processes that go on inside the Eagle Nebula as these beautiful structures are formed. And this is what we put together for you. And as soon as they're done adding awesome new features to the Inspiring Science Education website, all of this will be there for you to use completely free. And we're hoping that you'll take these materials and adapt them for use in your classroom. We know that the needs of every class are a little bit different. First of all, I know you're not all going to be working in English. And if you want to take this lab, you can duplicate it within the interface and replace all of my English with whatever your native language may be, or whatever the kids' language may be. You may also find that this math is just way too much for your kids to do. This was designed for older high school kids. If that's the case, and you have another way that you teach these concepts to your kids, pull out My Complicated Math and drop in what you'd rather see for your classroom, and then share. The entire idea behind the Inspiring Science Education portal is to make it easy for you to adapt our materials for your means, and then share what you've created with the entire community, because it takes all of us to create the educational materials that are needed to educate the world. Now, we've been going at this for about an hour, and I'm going to let you go and enjoy your day, your evening, whatever the rest of your day may be, in whatever time zone you may be in. And I'd thank you for joining us, and I hope to see you in the Inspiring Science Education Hangouts in the future and contributing to our portals online. Our next lesson is 2 weeks away, same time, same place. You can find everything listed on our Google Plus page for the Inspiring Science Education Hangouts. And our next lesson is going to be on the electromagnetic spectrum. So we're going to get to see what the universe looks like in all the colors of light. So thank you. And let's make a more scientific universe and a more scientific school. Thank you.